Good morning. Okay, so we'll just wait for people to join and then we'll start. Okay, let's start. So last class we finished chapter 4. Right, and so we were talking about the cumulative distribution function at the end of last class. So we finished chapter 4 and talked about the cumulative distribution function for discrete random variables. Okay, so this class we're going to start chapter 5 and talk about continuous random variables. And we're going to talk about probability density functions for continuous random variables. Okay, so let's start. So chapter 5 is titled Continuous Random Variables and Probability density functions. Okay, and so 5.1 is an introduction. Okay, so when the set of possible values of a random phenomenon is a continuous extent of real numbers, the value of the phenomenon is a continuous random variable. Okay, so this is an introduction to what's called a continuous random variable. Okay, so let's talk about probability density functions. Okay, the probability function f of x equals the probability of capital X equaling some fixed value little x plays an important role in a discrete random variable x. Okay. So let's look at this with an example. Okay, so let's say we shoot an arrow at a target, and f of x is equal to the probability that capital X equals a fixed value little x is the probability that the arrow is little x inches away from the center, rounded to the nearest. And so for each one, we're going to choose a different measurement. So for A, we're going to choose inch. Okay, so we have a target, and f of little x equals the probability that capital X equals little x is the probability that the arrow is little x inches away from the center, rounded to the nearest inch. Okay. So let's go to the whiteboard. Okay, so you have your target. Right, and then you have, okay, so you have the whole board there. Here's the target. Here's the target. Okay. You should shoot it with an arrow, right? So let's say, 0 inches would mean it hits the target directly. 1 inch would be like, if it was somewhere, I guess nearest inch would include the boundary here. So that would be like 1 inch, right? This would be, let's say, 2 inches. Don't mind the circle that I'm drawing here. These are circles. That would be another inch. So that would be 1 inch, 2 inches, 3 inches, right? I'm going to use, say, blue here. So you have 1 inch, 2 inches, 3 inches, and so on, right? Okay, so let's say we draw a histogram, a probability histogram, to represent the chances of the arrow hitting these different regions. Okay, so we ask ourselves, what is the chance that the arrow hits the target 0 inches away from the target to the nearest inch, right? So if it was a quarter of an inch away from the center, that would round to 0. So 0 does not mean 1 point. 0 means a region of space which rounds to the nearest inch to 0. Okay, and then there's 1, and then there's 2, and then there's 3, and then 4. Going to 10 here. Move some things around on my screen so I have room. Okay, so you have 5, you have 6, you have 7, you have 8, you have 9, and 10. Okay, and etc. Okay, so at 0, let's say we have a certain height for the bar there, and then let's say at 1, we have a higher bar, and 2, we have a lower one, and then 3, we have a lower one, and then 4, we have another one, and then 5, and then 6, and then 7, and then 8, and then 9, and then 10 is nothing. Okay, so the further out you go, the less likely you are to hit the target, right? So probably the one with the highest probability is 1 inch away, but it's to the nearest inch. So what that really means is, let's say, for instance, for 0 inches, it's really kind of this region here, right? It's the region that rounds to 0. And then the next region, for the next region, let's go with this green, right? So the pink is used to denote the inches away, but the next regions I'm doing is the regions of space which rounds, to this. So this green area here, this is the region that if you hit the arrow here, it rounds to 1 inch away, right? So this would be the green region here that I just drew, and the orange one would be 0, right? So if you hit an arrow anywhere in this orange region, the distance away from the center rounds to 0 inches, and then if you're anywhere in the green area, it rounds to 1 inch away, and so forth, right? And you keep going. Okay, and so like the next one, let's say we use brown. So for brown, if you're less than halfway between the two, right? And so if you're here, right? I'm shading now, I'm not using lines. If you're in this brown region of space, you round to 2 inches away to the nearest inch, right? And so forth. Okay. So So this is a probability histogram for that situation. So that's A, rounding to the nearest inch. Okay, so we round to the nearest inch there. Okay. For B, let's say we round to the nearest half inch. Okay, so we still have the same, same target thing. We have the target in the middle. We have, well, it's now not an inch. Now we're talking about half inch. So now this is a half inch away. This is 2.5 inches away. This is 3.5 inches away. This is 4.5 inches away. This is 5.5 inches away. I'm going to do one more. So it corresponds with this, that. This is 6.5 inches away, which means it's 3 inches away. Okay. And so now the numbers are representing the number of half inches. So this would be 1.5 inch away, 2.5 inches away, 3.5 inches away, 4.5 inches away, 5.5 inches away, 6.5 inches away. And so if you hit the dartboard in a region and around, you look at the distance away from the center and you round it to the nearest half inch. Okay, so now you make a histogram for that. You see, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now you have the the bars for these number of inches. It might look similar, but this will be a better approximation of the actual chances of hitting, these regions. Okay, so the goal is to really make these measurements smaller and smaller. So you have an inch, then you have a half inch, and then so you keep decreasing this, and so eventually you get a limit where the limit of these probability histograms will give you the probability density curve for the situation. So when you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is the limit. Okay, so it's the limit of the probability histograms. Okay, this is the limit of the probability histograms. Okay, so this is the limit of the probability histograms. And so we now do that. So let's say something like this. Okay, and so now the limit of the probability histograms, you take those bars and make them smaller and smaller. You make the increments smaller and smaller, and then you look at the heights at these numbers, right? And so you take all these different and you end up building the limit of the probability histograms, which is this graph. Okay, so this is the limit of the probability histograms. Let's go back to the word. Oops, that was the last. Here we go. Okay, so A, B is ½ inch, and C is the limit of probability histogram. Of probability histograms, okay? And so all three are illustrated on the whiteboard. All three above are illustrated on the whiteboard. And so the curve in C, no, that's not, I don't want copyright. The curve in C is called the probability density curve of the random variable capital X. And the limit of the histograms of the corresponding discrete random variables. Okay, so the curve in C is called the probability density curve of the random variable X, and the limit of the histograms of the corresponding discrete random variables. Okay, so that curve I drew in C, which is the limit of those bar curves, of those bar chart, of those histograms, is called the histogram is called the probability density curve of random variable X. Right? Each histogram is the histogram of its own discrete random variable. Right? So when you round to nearest inch, ½ inch, ¼ inch, ½ inch, each of those correspond with its own random variable, discrete random variable. And so when we find the probability density curve of random variable X, I'm just saying it's the limit of the histograms of the corresponding discrete random variables, one for each histogram. Okay. So the function defined by, I'm just going to see if anyone else is, okay, nobody else is trying to send. Okay. The function defined by this curve is the probability density function of capital X. Okay, I say a little bit more here, though not much. I'm just saying that the function that defines this curve, the function that would draw you this curve, that function is the probability density function of X. Okay, the curve is the probability density curve of X, and the function defining that curve, or defined by this curve, is the probability density function then. Okay, so now if we look at the probability that A is less than or equal to X, less than or equal to B, this is equal to the integral from A to B of f of X dx. Okay, and the probability that capital X is at most little x is equal to the probability that negative infinity is less than x, less than or equal to, less than capital X, less than or equal to little x. Yeah, okay, good. And that's equal to the integral from negative infinity to little x of f of X dx. Okay, it's the area under the curve. Okay, so in the next example, I'm going to illustrate this, and it should make complete sense. So you have the probability density function of x, f of x, right?
I have a question.
Yeah.
So you basically find the area of each rectangle on the curve.
But what? Repeat that.
Like you find each area of the rectangle on the curve. Is that
Well, so look. You have a histogram, right? Where
yeah.
let's say you round to nearest inch, right? This histogram is like an approximation of the PDF. Now you round to the half inch. This is a better approximation. Round to a quarter of an inch. It's a better approximation. And so if you take the limit of these, if you take better and better approximations and you take the limit of these approximations, you get the actual PDF. The PDF is the limit of those probability histograms.
Okay.
So instead of rounding, instead of saying what is the odds of hitting the target, let's say half an inch away, right? Which isn't perfect, right? You intuitively see how that would not be the exact thing, right? Because you're rounding, right? But then if you say a quarter, it's a better estimate, right? Because you're looking at smaller and smaller regions. And so then eighth and a 16th. So if you take the limit of those probability histograms, you're finding the exact PDF, which if you take the height at any point, not just one or a half or a quarter or 3/4 or 7/8, you take any point, since it's the limit, the height will give you the height it should be for the PDF. Now, if you want to find, the probability that the value in that example is between 3 and 5, you find the area under this PDF between 3 and 5. So that would correspond with the definite integral from 3 to 5 of f of x dx. That would be the probability that the distance from the center is between 3 and 5. Does that make sense?
Yeah.
Okay, so that's what we're doing. We're saying that the probability of an interval of a range of values of your continuous random variable is the area, correspondingly the area under this PDF, which is gotten by the limit of those probability histograms.
Yeah, now it makes sense.
Oh, okay, good. Okay, so example 5.1. Consider the experiment of selecting a number from the open interval 2, 4. So it does not include 2 or 4. Assume if subintervals I1 and I2 of 2, 4 are equal in length, the probability of the number being in either interval is the same. Let capital X be the number selected. Then f of x is equal to one half for 2 less than x less than 4 and 0 elsewhere. Okay, so consider the experiment of selecting a number from the open interval 2, 4, or assume if subintervals I1 and I2 of that interval 2, 4 are equal in length, the probability of the number being in either interval is the same. Let x be the number selected. Then the probability of then is not probability, just f of x, our PDF, is equal to 1/2 for x between 2 and 4 and 0 elsewhere. So let's look at this PDF. It's a very simple one. Okay, so okay, so we have values of little x and we have values of the f of x function. And so we're defining it to be if little x is between 2 and 4, the value of our PDF is 1/2. And then 0 elsewhere. So let's go with pink. So between 2 and 4, the height's 1/2. And then everywhere else, meaning including 2 and 4 in the elsewhere, the value of the function is 0. Okay, so that's the graph of y equals f of x for that example. Okay. Okay, so that's graphing the PDF, right? The situation we're looking at again is if you have the interval, you have the real line, and you have a subinterval 2, 4 of the real line. And so if you look at any two subintervals of equal length of that, the probability of the number being selected is the same. Okay, so you select a number at random here. So if I chose a subinterval, of length 1/8, let's say the interval was length 1/8, and I chose another subinterval also of length 1/8, then the probability of it being selected in either subinterval would be the same, right? That's the assumption. Okay. Okay, and this is the PDF, right? And so the reason why it's 1/2 is because we want the total area. We want the total area under this PDF to be 1, just like we had the sum of the probabilities to be 1 earlier for a discrete random variable. We want to say that the definite integral from -infinity to infinity of f of x dx is equal to 1. And so we're going to talk about this, right? And so since we want this to be 1, and since we have this kind of uniformness of this probability in that if you take any subinterval of equal length anywhere, the probability is the same. And so this PDF has to be uniform. It has to be the same everywhere. We need a constant for this. Okay, and so, but it only has positive probability between 2 and 4. And so really this definite integral from -infinity to infinity of f of x dx, it's only going to have positive values between 2 and 4. And the endpoints don't make any difference because they're only points. And so we're going from the definite from 2 to 4 of whatever f is, which is constant because of this assumption of equal probability. So we have some constant here, but we need this thing to equal 1 in the end. We need the entire area under this curve to be 1. So if we looked at the area, right? If we looked at the area under this PDF, since everywhere else is 0, there's no area. And so if we look at the space under this curve, its area, the area has to be 1. So the area needs to be 1. From the area is 1, we get that the height is 1/2, right? So if we integrate from this constant, instead of 1/2 here, let's say it's a c. And so the question is, what is c? And we get that c is 1/2. So if you integrate this, you get cx evaluated from 2 to 4. And so this is equal to c times 4 minus 2, which is 2c. And so what do we have? We have that 2c. We have the 2c is equal to 1. And so that implies that c is 1/2. Okay, so that's how in that example, we get that the height of the PDF is 1/2. Okay, but So what the main point was to show how you graph it, but I'm also showing you how you get the PDF here. Okay. Okay. Kishan, I don't know what you mean by the question. What do you mean is satisfy the interval?
I mean, like, it has to satisfy the interval of infinity and negative infinity. That's what I meant.
No, so you mean this? You mean the limits of integration?
Yeah.
So if you go from negative infinity to infinity, right? Well, you're integrating f over the entire real line. Okay. And the goal, what you need is that when you integrate this graph, this function from negative infinity to infinity, you get 1, because what you need is the area under the curve to be 1. That corresponds with a discrete random variable where you add up the probabilities of every possible value of x, your discrete random variable, and you get 1. Okay, so just like you would add finitely many probabilities or countably infinitely many probabilities and you're supposed to get 1, here you find that the area under the curve needs to be 1. And so knowing that this function is constant because of this uniformness of the probability, you get that the c, this constant value of that function between 2 and 4, has to be 1/2.
Okay.
Okay. Okay, so that is that example. Okay, so the graph of PDF is illustrated by board. Also is explained how you can find that the PDF is what it is defined as. Above. Okay, so you didn't have to be given that PDF, you could have found it. Okay, so 5.3, continuous random variables. And so let's start with the definition. So this is definition 5.1. A real valued function, capital X, defined on a sample space, capital S, with probability set function, capital P, is a continuous random variable provided there is an integrable function, little f, such that the probability that capital X is at most some fixed value little x is equal to the integral from negative infinity to little x of f of t dt for negative infinity less than x less than infinity. The function little f is a probability density function of the random variable capital X. Okay. Okay, so this is the definition. A real valued function a real valued function capital X defined on a sample space S with probability set function P is a continuous random variable. Provided there is an integrable function little f such that the probability of the value of your random variable capital X being at most little x is the integral from negative infinity to x of f of t dt for any finite little x. This means finite. This means little x is finite. The function f is the probability density function of the random variable capital X, which we defined earlier as the limit of the histograms, right? Okay. Remember, x, right, as a random variable x, let's go to the white. Well, so first, make sure to write this down. Okay, write that down. Capital X here is a random variable. So it's a function, right? A random variable is a function where the input is an input is a subset of the sample space, and the output is a number. So it's defined on the sample space, right? So I'm gonna go to the whiteboard. Right, so your capital X, which is your random variable, let's go brown. All right. You've already done this before, so it's not that interesting. So let's go with X. So this is your random variable, right? And so you input a subset of your sample space. So A is a subset of the sample space, right? Like an event. And then the output is a number associated with that event. Okay. And then and so then the probability set function P is saying, okay, we want a certain set of values of capital X as our input, and then the output is a number, right? The probability that capital X takes on values in that subset. Okay, so okay, and so if you take that number, right, and you were to like let me put it another way. Okay, so so if you had an event, a subset of the sample space, and you inputted it into X, it would output a number, right? And so then if you take, values of X, and you input it into a probability set function P, right? The output is also a number. And it's the number associated to these values of X, right? So if it's an interval, like if it's an interval, let's say 2, 4, then P of this would equal the probability that capital X was between 2 and 4. Right? And so the probability is a number associated to a certain set of values of X, and then the number, right? And so that number is the probability. It's called the probability. Those X values are between 2 and 4. Okay. 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 So the next section is 5.4. So I'm finding probabilities for continuous random variables. Okay, so let's call these the rules for finding probabilities for continuous random variables. First rule, the probability that capital X is equal to any fixed value little x, it equals 0 for negative infinity less than x less than infinity. This is a continuous random variable. So the probability that a continuous random variable equals any one value is 0. You need to look at an interval of values, let's say, to find a positive probability. So that's one of the rules. The probability that capital X is strictly less than little x is equal to the probability that capital X is at most less or equal to little x. And that's equal to the integral from negative infinity to little x of f of x dx. You need a dummy variable f of t dt. And this is for negative infinity less than x less than infinity. Okay, so since the probability of capital X taking on any fixed value is 0, then you can either include or not include this one value, little x, in this interval, right? So if you look at all the capital X values less than little x, or you include just one value, little x, into that, so now it's x less than capital X less than or equal to little x, these two should be the same because of 1, and they are. So, and it's equal to the integral from negative infinity to little x of f of t dt for any finite little x. It's the area under your PDF function for values of capital X up to or up to including little x. Great. The probability that A is less or equal to capital X less or equal to B is equal to the probability that A is less or equal to capital X strictly less than little b, which is equal to the probability that A is strictly less than capital X less or equal to B. And this is equal to the probability that A is strictly less than capital X strictly less than B. And that's equal to the integral from A to B of f of t dt. And this is for any x finite. So for negative infinity less than x less than infinity. Okay. So these four are equal because you're either including or not including the endpoints. And so you're either including or not including the probabilities of individual values. And so because of 1, right, the probability that capital X equals little a is 0. And the probability capital X equals little b is 0. And so you can include or not include them in these intervals. But anyway, probability of all four of these intervals is the depth interval from a to b of f of t dt for any finite little x. Oh, sorry, for a less than b. Right, for a less than b. So I'm just saying that this is less than that. Okay, good. So observe that the probability that A is less than capital X less or equal to little x is equal to the probability that capital X is at most little x minus the probability that capital X is at most little a. And so we saw something like this in another class because if you, let's go to the whiteboard. So I'm going to illustrate that I'm going to illustrate this on the whiteboard. Okay, this equation. Yeah, I'm going to illustrate that. Okay, write that down. Okay, so now so a to x. So if you were looking at so if you're looking at the x values between a and little x on the number line, so this is the real number line. That script R means real number line. And so if you want the probability that x was somewhere on this blue part, right? You could say, well, you know, what are the chances that it's on this green part, which extends all the way to the left to negative infinity on the real line, right? Where this is still little x, but now we don't stop at a, we keep going. We could ask ourselves, what's the probability of this? And then just subtract the probability of that, right? Right, so if we find the probability, that capital X is at most little x, right? The probability that it's in this green part of the real line, and we subtract from it the probability that capital X is at most little a, right? Then what we're doing is we're finding the probability of it being in the green region and not in the red region. That's the probability of the blue region. That would equal the probability that a is less than the value of capital X, which is less or equal to little x. I'm exaggerating the height. This little x, that's capital X. Okay, capital X is your random variable, your continuous random variable here. Sometimes it's discrete, but right now it's continuous. Capital X is your here a continuous random variable. Little x is a value, a number, a real number. Okay, so you see that you take the green region, you remove the red region, you get the blue region. So the probability of being in the green region minus the probability of being in the red region is equal to the probability of being in the blue region. Okay, so that's how we get this equation on the white over here. That's explaining this equation. Okay, and so now you just calculate those two probabilities and you subtract them and you get the probability of a less than capital X less or equal to little x. Okay, so the first one is the integral from negative infinity little x of f of t dt. And then you subtract from that the integral from negative infinity to a of f of t dt. Okay. And then by properties of the integral that you learned in calculus, this is equal to the def integral from a to x of f of t dt. Okay, so we just showed that this probability of this interval is equal to that def integral. Okay, note that the probability of a less than capital X less or equal to little x, right? That's equal to the probability of if you included a in the subinterval, right? It doesn't make a difference if you include it or not include it. It also doesn't make any difference if you include or not include capital X in the subinterval. So all of these are, all four of these probabilities are the same. And so all four of those probabilities are the same because they involve including or removing finitely many, only two values. In the subinterval, probability of any particular value is 0. So we're not changing the probability. And so we found that this is equal to this def integral. So all four of these are equal to that def integral. Make sense? Okay, so it doesn't matter if you include or don't include the endpoints, but technically these were defined, we found that these are equal to these correspondingly. And so the proof would use this one, right? You would use this one. And you would know that this first one equals this. And because of rule 1, you know, these other three are the same as this. And so all four of them are equal to that. Okay. Okay, so also observe that if you take the limit as C approaches 0 of the probability of X minus C less than capital X, less or equal to a fixed value little x. This is equal to the limit as C approaches 0 of the definite integral from X minus C to X of f of t dt. And now if you're taking the limit, that means that these limits of integration, this bottom one is approaching x. So that means definite from x to x would be 0. So the limit of these definite integrals is approaching 0 because the limits of integration are approaching the same value. They're both going to be x, right? And so if you integrate x to x of any function, it's going to be 0. Okay, and so this implies that the probability that capital X is equal to little x has to be 0. Okay, because if you're taking the limit as c approaches 0 here, the minus c is approaching minus 0, and so the probability this interval has to, the only thing it contains is little x. And so that means that the probability of capital X being the only value in this limit, little x, probability of capital X equal to little x is equal to 0. So this thing here, the thing on the left of this equal sign, this limit of this, right, is this probability, and it's equal to 0. Okay, so I'm going to write that. But so the probability that capital X is equal to little x is equal to that limit. Okay, it's equal to this limit because as c gets smaller and smaller, you're subtracting less and less. And so the only capital X that could be between this and this, including x, little x, is little x. So this is equal to this. This is equal to the limit of these definite integrals. The limit of these definite integrals is 0. So this has to equal 0. Okay. Okay, so that's how we get rule 1, that the probability of any fixed value of capital X has to be 0. Example 5.2. Question?
Yeah, so like c has to be greater than 0 in that.
Wait, can you talk louder? Sorry.
So c has to be greater than 0.
Little c?
Yeah.
No. No, I mean, you can approach 0 from positive or negative. So, you know, if you take a limit, right, here's the real number line, and you look at c, what was I thinking? C, okay, here's 0, right? And if you take values of c, okay, I gotta use a third color now. So let's say you look at, if you take values of c, right, and they're approaching 0, they could approach 0 from the left. They could be negative, right? So saying c approaches 0 does not mean that it has to approach it from the positive side. It could bounce back and forth. Eventually, c could be negative, right? Just because you're saying minus c, right? That doesn't mean the thing you're subtracting has to be positive.
Yeah.
Right? Like if you had 5 minus c is equal to 8, what is c equal to?
-3.
Did you say -3?
Yeah.
Right. So you see that the c we're subtracting is not negative here.
Yeah.
So So then you see here that the x minus c, you could be subtracting a negative number.
Yeah.
Okay, so c can be positive or negative. What matters is that c approaches 0. So the fact that c approaches 0 means that you get the conclusion that probability of capital X equals little x is 0. Okay. Okay. Let capital X be a continuous random variable with probability density function. F of x is equal to 2x for 0 less than x less than 1, 0 elsewhere. Find the probability that capital X is less or equal to 0.4. The probability that capital X is greater than 0.2. The probability that 0.2 is less than capital X, less than 0.4. And the probability that capital X is equal to 0.5. And the probability that capital X is less than 0.4. Okay, so we're going to find these 5 probabilities from this PDF of the continuous random variable capital X. Okay, so let's start with probability that capital X is less than or equal to 0.4. So we think about the integral this corresponds with. So this is equal to the integral from negative infinity to 0.4 of f of t dt, right? So don't just memorize the integral this equals. Understand that this is the area under your PDF F from negative infinity up to 0.4, right? So the x values up to 0.4, up to and including 0.4, are all the real values from negative infinity up to and including 0.4. And so you want the area under f of t from negative infinity to 0.4, right? And so you just want to find this. Now, the PDF is 0 everywhere other than between 0 and 1, right? So it's equal to 2x for x values between 0 and 1 and 0 elsewhere. So let's draw this. So we have a PDF here. Okay, so we have, I'm going to use a dummy variable t, and then here's going to be f of t. Okay, so between 0 and 1. So we have 0, and let's just exaggerate this as 1. And so we have, we have to, here's 1. Okay, so let's say we look at the graph. Of f of t here. Goes to 0. And then we have this. This is an open, doesn't include that point. And then here. It doesn't include the left endpoint either, but then 0 everywhere else. And so since it's not including 0, then we just plug it in for the other part. So this is the graph of y equals f of t. And this is 2. So this is a line segment from the origin to 1, 2. This is the point 1, 2. And that's because it's the graph f of x is equal, right? This is what I wrote on Word. This is equal to 2x for 0 less than x less than 1 and 0 elsewhere. All right, else for elsewhere. Okay, so that's 0. Okay, so it's 0 everywhere else, but between 0 and 1, the value of f is 2x, right? So the dummy variable is t. So if I chose t equals 1/2, the height would be 2 times 1/2. Okay, so the slope of this line segment is this line segment is on the line whose slope is 2. So that's why this has 2x here and here. Okay, so that's our PDF f. And so when we integrate, when we integrate from negative infinity to 4 to 0.4, our f of t dt, right? That's the curve of f of t is this. And so when I integrate this PDF from negative infinity to 0.4, that's a 0.4. Not in my sense, it's 0.4. So when we integrate this function, we'll find the area under this function from negative infinity to 0.4. So where is 0.4? So 0.4, 0.5 would be like in the middle. So it's a little bit to the left of that. So we have 0.4, which is right here. So we want the area under this graph from negative infinity to 0.4. And so the area under this graph would be, let's use green, would be the area of this region. Make sense? There's no area under the curve to the left of 0 because it's always 0 everywhere else, right? 0 everywhere else. And so there's no area here. The only area, non-zero area is here. And so that's the definite integral from 0 to 0.4 of our f of t dt. That makes sense? This is the only place with positive area from 0 to 0.4 by how we defined it. And so now that's equal to, well, f is defined as 2x there, right? So our dummy variable is t. So this is the definite integral from 0 to 0.4 of 2t dt. And so you integrate that, and you get 2 times t squared over 2, evaluated from 0, that's a 0, to 0.4. Okay, and the 2's canceled, 2 and 1/2 cancel, so you really get t squared from 0 to 0.4, so you get 0.16. Okay, and so the definite interval from negative infinity to 0.4 of f t dt is equal to 0.16. It's the green area here. Okay, so I'm just going to write this down here. This is equal to 0.16 as illustrated on the whiteboard. Okay, so next is the probability that capital X is greater than 0.2. Okay, well, the probability that capital X is greater than 0.2 is the probability that 0.2 is less than capital X, less than infinity. Okay, and so let's now look at this 0.2 less than x less than infinity on the whiteboard also. Let's see if I can copy this. I don't know if this is going to work, but nope. Okay, so I kind of like that picture, so I guess I'll redraw it quickly. Okay, so I'm going to redraw this quickly. So you have this axis, you have this axis, you have that. So the t is the dummy variable. T, the dummy variable, f of t here. Okay, we have the graph, which is pink. That's just on the x-axis, and then you fill this in, and that's the left, right? Okay, so this is y equals f of t. This is 0. This is 1. This is 2. Right? Okay, so we have that. And now the probability that 2.2. Probably that 0.2 is less than capital X, less than infinity, positive infinity. If it doesn't say a plus or minus sign, it's plus infinity. Well, this is equal to definite integral. This is the area under the curve f from 0.2 to infinity. So 0.2 is here, right? Oh, blue, okay. Okay, so 0.2 is here. And so you want the area under f from 0.2 to infinity. Well, there's 0 area here. And so the positive area is from 0.2 to 1, right? Let me just check. This is green, okay? So you want this area here. So the amount of space this green region takes up is the area under f from 0.2 to infinity, positive infinity. So this is equal to the definite integral from 0.2 to 1 of f of t dt. Remember, our f of x is equal to 2x for 0 less than x less than 1, 0 elsewhere. Right? And so this is the definite integral from 0.2 to 1 of 2t dt. And so this is equal to 2 times t squared over 2, the antiderivative of t, and then evaluated from 0.2 to 1. The 2.5 cancel, you get t squared from value from 0.2 to 1. You get 1 squared minus 0.2 squared. That's equal to 1 minus 0.04, and that's equal to 0.96. 0.96 decimal points. Okay, so you get 0.96. It's equal to 0.96 as illustrated on the whiteboard. Okay, the next probability is the probability that 0.2 is less than x less than 0.4. Well, we know from before this is equal to the definite integral from the left one to the right one, and we have positive probability at all those places, so we can keep the interval the same without looking at a subinterval. Right, and so this is and so PDF F there, I'm writing in more steps than I have to, 0.2 to 0.4, and f of t there is 2t dt, and so you integrate that, and so you get 2 times t squared divided by 2, evaluated from 0.2 to 0.4, and that's equal to the 2 and 1/2 cancel, and so you get t squared value 0.2, 0.4. So you have 0.4 squared minus 0.2 squared. You have 0.16 minus 0.04, which is equal to 0.12. Okay, and so that's the probability there. And so now the probability that capital X is equal to a fixed value 0.5 is equal to 0, because a continuous random variable probability of it taking any fixed value is 0. The probability that capital X is less than 0.4 is equal to, so just like before, saying it's less than 0.4, actually, saying it's strictly less than 0.4, it doesn't change. It's the same as the probability of X less or equal to 0.4, right? We can add or remove one particular value. We already found this is equal to 0.16. And this is from above, right, from right here. So we just add one single point. The probability of X equaling the 0.4 is 0. So this is equal to this, and we already found that this is 0.16. Okay, and so that's all of example 5.2. Here's another example. Example 5.3. Suppose in a region, the daily rainfall in inches is a continuous random variable, capital X, with probability density function, f of X, given by f of X, which is equal to bracket is equal to 3/4 2x minus x squared for 0 less than x less than 2 and 0 elsewhere. Okay. Okay, so we have daily rainfall in inches, the value of that, the continuous random variable capital X, and this is the PDF. Okay. So the problem is find the probability on a given day in this region, the rainfall is A, not more than 1 inch. Okay, so the probability that the rainfall is not more than 1 inch. I don't have to write all this out, but I'm going to be doing it so you understand it. Probability of rainfall is not more than 1 inch. The amount of rainfall is given by is described as capital X. So not more means it's less than or equal to 1. So this is the probability capital X is less or equal to 1, and that's equal to the integral from negative infinity to 1 of f of t dt, where t is our time variable. I guess we could use x. We can use x. Okay, and so then we're going to calculate that. And so that's equal to, well, it's 0 everywhere other than between 0 and 2. So just like before, if it's only non-zero between 0 and 2, but you're integrating from negative infinity to 1, the only values in the interval from negative infinity to 1 we care about is from 0 to 1. So we integrate from 0 to 1 of this PDF. And this is dx. And so you calculate that integral and you get this is equal to 0.5. Okay. Maybe you want to see me calculate this integral. I'm going to maybe do this on the whiteboard. Okay, so now I'll just show you that this integral is equal to 0.5. This is just calculus. Okay, so you integrate from 0 to 1 of the PDF there, 3/4 times 2x minus x squared. This is lowercase x, okay, dx. Okay, so you integrate that. So to integrate this, you move the 3/4 outside of the integral. And so you're integrating now this from 0 to 1 2x minus x squared dx. Okay, and then now this is equal to 3/4 times, now an antiderivative of 2x minus x squared is x squared minus x cubed over 3. If you take the derivative of that, you get 2x minus x squared. Okay, and you're evaluating it from 0 to 1. Okay, so if you evaluate that from 0 to 1, you have 3/4 times. Now, if you plug in 1, you get 1 squared minus 1/3, because 1 cubed over 3 is 1/3. Minus, plug in 0, you get 0 squared minus 0 over 3. And so this is equal to 3/4 times, well, 1 minus 1/3 is 2/3, and 2/3 minus 0. So that becomes 2/3. What's in the bracket there? You get 1 minus 1/3 is 2/3. This is 0. 0 minus 0 is 0. 2/3 minus 0 is 2/3. Okay, so then you get this times this. The 3's cancel, and you get 2 over 4, which is 1/2. Okay, and 1/2 is 0.5. So this definite integral is equal to 1/2 or 0.5. Okay, so I'm showing you the calculation here. Okay, so that equals 0.5. Okay, so I calculated the definite integral is calculated on the whiteboard. Okay, part B. The probability that rainfall is greater than 1.5 inches. So the probability that the rainfall is greater than 1.5 inches, capital X is the amount of rainfall, so probably X is greater than 1.5. Okay, and the probability that capital X is greater than 1.5 is 1 minus the probability that capital X is not greater than 1.5, which means capital X is less or equal to 1.5. Okay, and so that's 1 minus the definite integral representing that probability. Well, remember our PDF is only non-zero between 0 and 2. And so if we're looking at all X values up to and including 1.5, it's really between 0 and 1.5. We start at 0 and then we go to 1.5 of our PDF f of X. And our PDF f of X is this. Yeah, but okay, I want to write f of X here. Okay, and so this is equal to 1 minus this f integral. Instead of f of X, I'm going to put this, because that's what f of X is, between 0 and 1.5. And so now this is going to be, I'm going to substitute this for what it is, which is that, in between 0 and 1.5. And so now you calculate this definite integral, and you get 1 minus 0.84375, which is equal to 0.15625. Okay, and so then you're done there. So you just calculate this definite integral, 1 minus that. Okay, you can calculate this very similar to how I calculated that on the whiteboard. Okay, and then C, probability that the rainfall is between 0.5 and 1.5 inches. So since capital X represents the amount of rainfall, this is the probability that 0.5 is less than capital X, less than 1.5. Okay, and so this is equal to the definite integral from 0.5 to 1.5 of the PDF, which is defined there to be this function, and then dx. Okay, and so then you just calculate that You get 0.6875. Okay, I'll put a 0 here. That's 0.5. I don't know, so does 0.5 look better than 0.5? Maybe. Okay. Okay, so then there you go. So that's C. And then D, what is the probability that the rainfall is exactly 1 inch? So the probability that the rainfall is exactly 1 inch is probably capital X is equal to 1. And so that's equal to 0 because at capital X is a continuous random variable, right? So the amount of rainfall is a continuous random variable, capital X. So the fact that it's continuous means the probability that X taking on any particular value is 0. That's one of the rules, the first rule that we had earlier. E, the probability that rainfall is less than 1 inch is equal to the probability that capital X is less than 1. And the probability capital X is less than 1 is the same as the probability capital X is less or equal to 1. And this is equal to what we found earlier. We found this, so at most 1 inch, we found that this was equal to 0.5. So that equals 0.5. Okay, so probably the rainfall is not more than the probability that is not more than 1 inch or less or equal to 1 inch is the same as probability less than 1 inch. Okay, 0.5. Okay, good. Okay, so that's that entire example. Okay, so now let's look at another example. And so this example is this, a third, where we think about a third type of random variable. Okay, so we've talked about discrete random variables. Okay, so note, you've talked about and have seen the existence of both discrete and continuous random variables. Okay, not only have we done theoretical examples, we thought of real life situations that illustrated the existence of both discrete and continuous random variables. Okay, okay, so the question comes to mind, is there another type of random variable that is neither discrete nor continuous, right? Are all random variables either discrete or continuous, or are there random variables that are neither? Okay, and so in this example, the goal of this example is to show that there are random variables that are neither discrete nor continuous. Okay, so that's the goal here. So we're going to talk about a random variable, and then we're going to show that it can neither be discrete nor continuous. And so that means that there's exists other types of random variables. Okay, so let's look at this experiment. Okay, so the experiment is toss a coin. Okay, if heads, the player gets 10 ounces of beer. If tails, let me put it this way, if heads, the player gets 10 ounces of beer. If tails, the player presses a button and receives anywhere between 0 and 10 ounces of beer. Let capital X be the amount of beer received by the player in the experiment. Okay? And so the question is, or the problem is, explain why capital X is neither a discrete nor continuous random variable. Okay. Okay, so you toss a coin, and there's two possibilities, right? We toss a coin, it's heads or tails. So if it's heads, the player gets 10 ounces of beer. Simple. If tails, the player presses a button and receives anywhere between 0 and 10 ounces of beer. Let X be the amount of beer received by the player in the experiment. Okay, now let's say between 0 and 10 ounces of beer means it could be 0 or 10 also when you press the button. Okay, but it actually doesn't matter. It could be either. Problem, explain why X is neither discrete nor continuous random variable. So there's two things we want to show. So one, why is capital X not a discrete random variable? Okay, so can someone answer me that? Why is X not a discrete random variable? Okay, so I'm going to give you hints, and then the more hints I give, the less impressed I am if you know the answer. Okay, so the answer is, so one of my hints, hint one, is what is the set of possible values of capital X? Right? What values could capital X take? X is the amount of beer received by the player in the experiment, right? If you flip heads, X is 10, right? And if you flip tails, what is X, right? So what is the set of possible values of X? What does that tell you about a random variable?
Professor?
Yeah, Ahmed?
That it's not infinite?
That it's what?
It's not infinite.
Well, what are the possible values of X?
So we have from 0 to 10, right?
Yeah, inclusive, right?
Yeah.
Because it could be 10 because heads, right? So X, the set of possible values of capital X are all the real numbers from 0 to 1 inclusive, right? So what does that tell you about your random variable capital X?
That it's not a discrete random variable.
Why?
Because it's not infinite. Because it's finite.
Because it is infinite, but it's of a continuous extent infinite. So our set of possible values of capital X, if this is the real number line, right? This is the real number line, and we look at the possible values of X, those possible values range from 0 to 1 inclusive, right? This set of values, right? These values are, these are all the values 0 less or equal to X less or equal to 1. This set is of a continuous extent, you'd say. Okay, it's not a finite amount, and it's not a countably infinite amount. It's not a discrete amount. All right. So this set is of a continuous extent. That means it's not discrete, right? It's not discrete, but it's also of a continuous extent. Does that kind of make sense?
Yeah, it does.
Okay, so since the sample space, right, the space of possible values of capital X is of a continuous extent, that means X cannot be a discrete random variable, right? So the set of possible values of X are all the real numbers from 0 to 1 inclusive. That set of possible values of capital X is of a continuous extent. That means that the set of possible values of capital X is not a discrete set. That means, so that tells you that capital X is not a discrete random variable. That makes sense, Ahmed? When you characterize a random variable as being discrete or not discrete, right? You look at the sample space of the experiment, right? And you ask yourself, how large is the sample space? How large is that set, right? You think about the size of the sample space. Either the size is a finite amount, like 5, 10, 7, a million. Those are all finite values. So either your sample space is finite, its size is finite, which means it's discrete, or you could say that even though the sample space is infinite, you can list everything in your sample space. So if your sample space was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? That would be a countably infinite sample space. It would still be a discrete, X would be a discrete random variable, okay? But if your sample space are all the real numbers from 0 to 1, you cannot list all the real numbers. You cannot put all the real numbers from 0 to 1 inclusive in a list. You can't say 0, 1/8, 1/10, 0.7, pi, pi over 8, and you can't list all the real numbers. There's so many real numbers between 0 and 1 inclusive that there's no possible list you can make that would include all of them, even though they're both infinite. There's larger infinities and smaller infinities. So this capital X has, as from its sample space, it has its sample space, which is not discrete, right? The sample space is not a discrete set. And so the random variable X is not a discrete random variable. So what I just answered here in 1 is why X is not a discrete random variable. So with this experiment, with this capital X, we have an example of a random variable that's not discrete. So Kashan, just to speak out loud, what's your question?
Yeah, so I was saying that X is not like a continuous random variable.
First, so far I've just said X is not a discrete random variable, right? Kashan?
Yeah.
Right, so far I don't want to jump ahead. I'm about to do that, but you see, right? I'm talking about why X is not a discrete random variable, right?
Yeah.
Okay, 2, I'm asking the question, why is capital X not a continuous random variable, right? The goal is to show that there exists, from this example, to conclude that there exists random variables that are neither discrete nor continuous. And so this is an experiment with a random variable that we're showing is not discrete and not continuous. So we've shown it's not discrete. Now we want to show it's not continuous. So Kishan, do you want to say why it's not continuous? Or do you have a question?
No, I want to. The answer is like because f so p x equals 10 is equal to 0, so that's why it's not.
Wait. Okay, so you're on the right track, but wait, almost. So let me ask you this question. What is you said x equals 10, right?
Yeah.
But what is the probability that x equals 10?
Is it like 1/2?
So why'd you say 1/2?
Because if you like toss a coin and Oh, and what's the probability of getting heads? So it's 1/2.
Good. Okay. Well, so we're close. Probability of heads is 1/2, right? So in the experiment, if you flip heads, the player gets 10 ounces of beer, right? Okay. Now, if you flip tails, the player presses a button and receives anywhere between 0 and 10 ounces of beer. And I was saying inclusive, right? So I'm including 0 and 10 as possible values. Okay. So if you press the button, you could get 0, you could get 10, you get somewhere in between. So you kind of have a chance at getting 10 ounces still from tails. So the question was, what is the probability that x is equal to 10, right? And so the answer to that, you're very close. You said the probability that x equals 10 equals 1/2. I want you to say something close to that. Can you amend your answer?
So it's like greater to equal to 1/2.
Good. Exactly. Probably that x equals 10 is greater than or equal to 1/2. Correct. Right? So the probability capital X equals 10 is greater than 1/2. But what does that tell you about the probability that x equals 10? Kishan,
Okay, so
I give you a
it's
chance here. So what do you want, right? What is the goal? You want to show x is not a continuous random variable, right? And so why are you looking at the probability x equals 10 to do that?
because it's like because it felt like the axes were continuous, and then that's why it's like p of x equals 10 equals 0.
Read the first, see here when I wrote the rules for finding probabilities for continuous random variables, right?
Yeah,
Read for me the first rule.
p capital X equals 0.
No, that's not what it says. Read again.
So p p the p parentheses capital X equals x equals 0.
Right, the probability capital X equals some fixed value little x is equal to 0, right?
Yeah.
Okay, so without reading the equation, what does that tell you?
So the capital X is capital X equals 10, and then
It's saying the probability that your continuous random variable being any fixed number, any number equal to any particular number is 0, right?
yeah.
Okay, now how does that apply to this example? That's in order, if you have a continuous random variable, that has to happen, right? But now the fact that the probability of x equals 10 is greater than 1/2, what does that tell you? How can you deduce from that x is not a continuous random variable? Using rule 1 that I just said there. Okay, so we're at a time, so I have to quickly say the answer so as I can in class on time, or like close to on time. So the probability x equals 10 is greater than 1/2. Okay, that tells us that the probability that x is equal to 10 is positive, right? Because 1/2 is positive. 1/2 is greater than 0. Probably x equals 10 is greater than 1/2, which is greater than 0. So that tells us probably x equals 10 is positive. So that also tells us that the probability that x is equal to 10 is not equal to 0, right? If it's greater than 0, it's not equal to 0. So the probability that x equals a fixed number is not equal to 0. It's supposed to. If you have a continuous random variable, then the probability that x equals any fixed value has to be 0. But here, it doesn't equal 0. That contradicts x being a continuous random variable because it contradicts the first rule of x being a continuous random variable. And the rule I said earlier. Okay. So thus x is not a continuous random variable. So by the way x is defined, it fails to be a discrete random variable, and it also fails to be a continuous random variable. Okay, and so our conclusion from this example is that since capital X is neither a discrete nor continuous random variable, there exists random variables that are neither discrete nor continuous. Okay, so we actually we're not seeing all random variables from these two, but we at least see the existence of other such random variables. Okay, so that's the end of 5.4. Okay, so we finished 5.4 now. That's good, and so we'll start 5.5 next class. So keep in mind that the homework is due tomorrow. No, not there. Wait. Oops. Close this. Okay. Homework 5 is due tomorrow, right? So this is due next class. Homework 6 is up to including 5.6. So we're not up to there yet. So I'm not assigning that yet. So homework 5 is due tomorrow. Okay, that's homework 5. Homework 6 you don't have to worry about yet. So just homework 5. It's due tomorrow. Oops. Right, I already signed it. I'm just reminding you. Sorry, I've got to find it. Okay, so reminder, homework 5 is due tomorrow at the start of class. Okay, on Wednesday, 8/4/2021. Today's Tuesday, right? Yeah, okay. Okay, so we'll stop there. And I'll see you tomorrow. So remember, homework 5 is due. I'll see you tomorrow. You also your exam grades, right? Okay, Kashan, do you have another question or the whiteboard?
Oh yeah, we have to save the.
Yeah, I got it. The PDF,
Okay.
the whiteboard. Thank you. Okay, so we'll stop there. Okay, see you all tomorrow morning. Bye. Thanks for being here.